Good evening everyone, I am Mr. S. Thank you for joining me for this video where we are examining for the first time the root test. It's an excellent test and I like this. We would utilize this for series with the nth powers, and I'll talk about what that is as we look in the examples. In all instances, generally you're looking here for a series from 1 up to infinity, the n values. Everything looks and examines here with regards to limit. Let L represent that limit. Limit from n approaching infinity, we have this nth radical absolute value of a n. What you're doing here in terms of the test, you're looking at something of this nature, 1 up to infinity. The beauty of this test is it sorts out many things for you in terms of absolute convergence and all of that. If L were equal to 1 with regards to this test, the limit value is equal to 1, it's inconclusive. There's no need for you to do the dart test, as I like to call it, which is the ratio test. The ratio test and the root test would give you both a L value of equal to 1 and they would be inconclusive for that specific situation. But the beauty lies in this test with regards to this. If L is less than 1, we have a situation which is convergent, but automatically with regards to this you'll have absolute convergence. So that's the beauty of it. If L is greater than 1, we have a situation of divergence. This version of that, as you know from the previous video, you wouldn't even have to bother with any conditional determination. It would be divergent regardless. So that right there is conclusive for me and I like this test. Remember, the root test, everything runs and stems off this limit. Limit as n approaches infinity, we're looking at the nth root of this item right here, which is your series function, and we would go from there. L equals 1, inconclusive. L less than 1, we have absolute convergence, and in general convergence, L greater than 1, we have divergence. What we want to do in this video is examine everything with regards to 4 examples, and I promise you they're beneficial examples. We're looking at this, n equals 1 up to infinity, 4n plus 5 divided by 2n plus 3 all to the power of n. This right here is what I'm talking about, the nth power, series with this nth power. Then you would utilize a root test and it would be a good idea. You have to evaluate all of this rational function, the rule with regards to that limit, and you would do it. You would bring everything right here, and this would be right here 4n plus 5. But I want to, before I do this, tell you something very important. This right here is this right here, and it's always your an term. Look right here, the limit is always the anth term. This here, your rule is your anth term, because depending on your n value, this will always give you your term in terms of that sequence or that series, the anth term. In all instances, this always is your an term, which feeds into your function. When you're looking at this, utilize laws of radicals and exponents. N root x to the power of n is no different than x to the n over n, which is no different than x to the 1, which means this can cancel out with that, and you've suddenly lost the radical and you have lost that exponent. Everything has become easy. You're just looking at the limit evaluation or the limiting value of this function right here. Limit as n approaches infinity, you're looking at 4n plus 5 divided by 2n plus 3, but divide each as if you're doing a horizontal asymptote determination, or you're doing some sort of limit evaluation where you divide the numerator and the denominator by the highest order degree of variable exponent, which here is n. When you do that, you get a 4 plus 5 over n divided by 2 plus 3 over n. Limit as n approaches infinity, these zero out, but you'll have 4 over 2, which is equal to a 2. That 2 represents your L value. Here you're getting an L value of 2. Since this L value here is larger than 1, we're looking here at a good case of divergence, and this series is divergent. Our next one is n equals 1 up to infinity, 5 plus 1 over n to the power of n squared. This right here is an nth power, a series to the nth power, so you can use the root test. This here represents an. You can view it as this and it would feed into your limit determination. Limit as n approaches infinity, you're feeding all of this, 5 plus 1 over n to the power of n squared, all to the power of root n, or you can say all to the root of n. Remember laws of exponents. You're really looking at some sort of item here, which is this function to the power of n squared to the root of n, which is like that. You know, the property of radicals, exponent a or m is really the m root of x to the power of a. That's exactly what I have. When I'm looking at this, I'm really looking at this item right here, my rational function to the power of n, because n squared and n simplify to just an n. That's a good thing right there, because suddenly this entire expression has simplified and you can eliminate the radical, because n squared divided by n gives you just this 5 plus 1 over n to the power of n. Now this is my limit n approaching infinity. Remember, when you have a rational function, simplify it before you do your limit evaluation. Always do that. This is really a no-brainer. Limit as n approaches infinity, this zeroes out. You're really looking at just 5 to the power of n, which is really 5 to the power of infinity, which in all instances is the divergence. And that right there would be a good case of divergence, a true divergence. When you're looking at this function to begin with, you could have really have seen, I'm looking at a very relatively large whole number plus an item here which is negligible. As these n values get large, this will always zero out. I'm looking at a whole number, a good size whole number, always to a very large exponent, and I know I would have a sum here, a sum of the series which would truly be divergent, and that's what we have. The root test confirms that we have a divergent series. Our third question will make for an interesting example. N equals 1 up to infinity. We have n squared divided by 4n squared plus 1 all to the power of n. Again, this is a series with the nth power, so we are using the root test. You know this right here represents your an term, which will feed in right here. You're looking at a limit evaluation of this. You have n squared divided by 4n squared plus 1 all to the power of n. But remember, the laws of exponents and radicals, this cancels out with that. You're really looking at just a limit evaluation of something easy, which is n squared divided by 4n squared plus 1. You want to find the limiting value of this function, which is really the same as a horizontal asymptote determination. You divide the numerator and the denominator polynomials with the highest order degree of variable exponent. You're dividing everything here by n squared in the numerator and everything here in the denominator by that n squared. When you do that, you have limit as n approaches infinity. You end up seeing a 1 in the numerator. Here in the denominator, you get a 4 plus 1 over n squared. You're dividing that by n squared. This zeroes out. You end up seeing just a 1 over 4. Your L value here is 1 over 4. L is less than a 1. Therefore, you're looking at a series which is convergent. Remember, at the very beginning, I told you the root test here. In terms of this series, you'll obviously have absolute convergence, and the root test will already be confident, and it will confirm you that absolute convergence. This question is done, and you're seeing the root test is not very hard. You just have to be wary and careful with your limit procedure. If there's anything hard here with regards to the root test, it's the limit evaluation, and that's about it. This right here represents our last example. N equals 2 up to infinity, n divided by natural log of n to the power of n. This to the power of n applies to the denominator. Why is it 2? Because if you had a 1 here, natural log of 1 is a 0. You would make the function undefined by bringing a 0 in the denominator. Hence, we're looking from 2 up to infinity. In all these examples, we're not expanding out the series. We're just applying the root test for the basic convergence and divergence determination. Remember, you're looking at now everything with regards to a limit of this, n divided by natural log n to the power of n. Now you can't always cancel out the roots because sometimes not everything has a power. But what you can do is separate everything using the properties of radicals into their own radical expressions, and that's exactly what I've done. When I've done that, I've brought here n to the power of 1 over n in the numerator, and now this can cancel out with that, and I'm looking at natural log n in the denominator. You see how everything has simplified to that, and I will run my limit evaluation utilizing that expression. This right here is exactly where being able to do your limit correctly will apply, because this is not a easy limit with regards to the numerator. You know, n approaching infinity, natural log of n. In the denominator, you'll always have natural log of infinity, which will be infinity. That you know. The denominator will always become infinity because natural log of a large number is a large number. Anyhow, we're looking at this. Let's look specifically at that. You're looking here at an extremely large number to the power of 1 over infinity, which is an extremely small number. In essence, you're looking at a large number to a very small exponent. And what would that be? You can do a calculator approximation. Let's take a large number as 10 exponent 50. I have 1 exponent 50 here. I can save that in terms of its reciprocal. That's 1 to the power of minus 50, and I'll save that because I'll represent this exponent power. I'll take that same number, 10 exponent 50, and I'll apply it in terms of exponent to that saved value, and look what will happen. You get a 1. What that tells you, when you're looking at a large number to a power of a very small number, you're always approaching 1, which means here in the numerator, you're approaching 1. You're looking here at limit as n approaches infinity, 1 divided by infinity, which is an extremely large number in the denominator. You'll zero out. What does that tell you? Here your L value is equal to 0, but 0 here is less than 1, and you're seeing here convergence. So this right here would be a case of convergence for this specific series here. Again, this right here was the hard part, n to the power of 1 over n. This right here very likely is a case n to the power of 1 or n, or x to the power of 1 or x, y equals that, is a probably a classic case of you approaching a horizontal asymptote y equals 1. As your x values are approaching infinity, your function is some way approaching either from above or below this horizontal asymptote y equals 1, hence you're getting a 1 over here with regards to that numerator limit. But the value here is 0 in terms of the L value. You have convergence, and that brings us to the end of this video. Remember the root test: L less than 1 convergence, but you have absolute convergence. L greater than 1 you have true divergence. L equals 1 you have inconclusive test. Even if you utilize a dart test or the ratio test, the Allenbert's ratio test, you will still be inconclusive. Keep that in mind. Thank you for watching.